We've got scheduled today for a oh a lecture that I did last week, right? So what I'm going to do is split the review and do half today and half next week, and then the exam on this material will be 2 weeks from today, on the 14th, just like it's in the schedule. So I'm only going to do half the review, and then we'll get to the lab. We'll talk about the lab first. I think we'll have enough time to do sort of an intro. And if you need any more documents, I didn't open up the lecture documents. They're here in a pile. Next week we're going to do this lab, molar mass by freezing point depression. So before you leave, grab one of these. You'll be ready for next week.
I got the last one.
Did I hand that one out already? No? Okay. All right. Yep. For
That, I guess, if somewhere I need to grab it or not.
actually, there are a couple of sheets stapled to the Boyle's Law today, but you're welcome to take as many as you need, because if you're not an old hand at drawing graphs, you'll probably mess one up and have to start over.
Yeah.
And then the molar mass by freezing point depression also has a graphing activity in it too. All right. So let's review chapter 7 and 8. Number 1. In which of the following groupings are the three terms closely related? It doesn't say what the relationship is, so you have to figure that out from the selections that are available. If we look at each one in turn, A says kinetic energy, energy of motion. Those are identical. Two ways of saying the same thing. Cohesive force. Remember we were talking about cohesive and disruptive forces. Which one is assigned to kinetic energy? Disruptive force. The higher the kinetic energy, the more disruption. So A doesn't fit because the cohesive force is not associated with either of those first two terms. Potential energy and energy of traction. Disruptive force. That's, if we had put disruptive in A and cohesive in B, then A and B would both be good. But neither one of them are, because they're swapped. C says kinetic energy, electrostatic interactions, and disruptive forces. Electrostatic interactions are part of potential energy. Those forces that attract one molecule to another are electrostatic. Kinetic energy is the motion involved, so they're kinetic energy and disruptive forces in C are together, but electrostatic interactions are not. So, how about D? Potential energy, electrostatic interactions, and cohesive forces. Those are all part of the same description. That's why D is the best answer for 1. Let's see. Who came in? Let's see. Drill down to P. All right. Number 2, the phrases particles close together and held in fixed positions. B. Oops. That's not what I want to do. 2. All right, what are we describing? If you look at the answers, we're describing phases. So what phase is described by particles close together? That could be a solid or a liquid. But when we say fixed positions, that can only be a solid. It completely fills the container. Okay, so you've got 2 of them. Sorry, I didn't read the whole question. The first one is solid. The second one completely fills the container. That's a gas. It expands to fill the space available. So solid and gas means B. Okay? All right. How about C? Excuse me. I don't know what's wrong with my brain today. Number 3. How many times larger in size is the atmospheric pressure unit than the millimeter mercury pressure unit? What you need there is to think of it as a conversion factor. If you're going atmospheric pressure, 1 atmosphere, which is equal to how many millimeters of mercury? 760. So the ratio there is 1 to 760. That's why the answer is C. It's just an odd way of wording a question. How about 4? Indicate what the missing word is in the following statement of Charles' law. Remember Charles' law? What's the relation? What 2 factors, what gas parameters are addressed in Charles' law? Variables. Remember, we can describe a gas with pressure, volume, temperature, and moles. So which 2 of those are assigned to Charles' law? Nobody has a clue. Volume and temperature. That's Charles' law. So, the volume of a gas sample is what proportional, direct or inverse? When you see this relationship, a quotient equal to a constant, they have to be directly related. Because as one goes up, the other one must go up in order to maintain that constant. So they're directly proportional. And what units of measure do we have to assign to temperature? We can't use Celsius, right? We have to use Kelvin. Does anybody have a clue why?
The higher scale unit, maybe.
It has to do with the sign. Celsius can come through as a negative value. And if you stick a negative in there, that messes with your constant. So we need Kelvin, which has no negatives. It starts at absolute 0, and all the values are positive. So the answer is B. They're directly proportional. Wait a minute. Oh, yeah, at constant pressure, the volume of a gas sample is directly proportional to its Kelvin temperature. All right, number 5. The correct form of the equation for the ideal gas law. We normally write the ideal gas law this way, just for convenience, and for printing it in texts, because typographers don't like to set type that has fractions in it. That adds a complexity that they would rather not deal with. So we write it in a straight line like this. PV equals nRT. That's A. All right, 6. When do you use the ideal gas equation? When you're only given pressure, volume, moles, and temperature, any combination, at a particular point. You don't know before, you don't know after, you just know where you are right now. That's when you use the ideal gas equation. Any of the other laws, Boyle's law, Charles' law, Avogadro's law, or the combined law, use those when you have a before and after situation. If you're given parameters for before, parameters for after, missing one, then you can use the combined law. I imagine you could use the ideal gas equation for before and after as long as you had enough information, right? All you need to use the ideal equation is pressure, volume, moles, temperature, and you can leave one of those out and solve for it. Okay, what is the volume in liters occupied by 2.12 moles of nitrogen gas at 0.745 atmospheres and a temperature of 55 degrees C? Is this a before and after or an ideal gas situation? Are you given 2 values of moles, 2 values of pressure, 2 values of temperature? No, you're only given one. That's ideal gas equation. So if we're going to use that one, we're going to need a value for, well, I'll just put it over here. I set it up like a table so I can extract information from the problem and get it in the right place. 2.12 moles. Now, does it matter that it's nitrogen?
It does not matter.
No, not for our purposes. It only matters, the gas identity only matters if it's involved in a chemical reaction. Then you have to deal with it. But in this case, it could be any gas. 0.745 atmospheres. Okay. And temperature, 55 C. All right, what do we have to do? This is our unknown right here. We have to change this one to Kelvin, don't we? So how do you do that? Okay, so that's 328 K. All right, so are these in the correct units? Well, K is now, we know that one. How about this one?
That's fine.
Okay, and this one?
That's fine.
Okay. With these units, what is R? Remember that value? Do I have that in the document? No, I don't. Okay. So let's solve for V. Like that, okay? So now we can put in our values. I'm going to leave the units out because we've determined that they're correct. So the moles would be 2.12. R is 0.08206 liter atmospheres per mole K. That determines what those units have to be. That constant. Liters, volume, atmospheres, pressure, moles, amounts, and K temperature. And then pressure is 0.745 atmospheres. Okay, so all we need is a calculator. We've done all the hard work up to this point. The rest is just number crunching.
Plug and play.
Yeah. And point. Oops, I left something out. And nobody stopped me.
Oh, perfect.
Temperature. All right, let's try that again. 2.12 and then 0.08206 and then 328 divided by 0.745. And that's volume. Let's see, my calculator says 76.59227
Just round up.
liters. Okay. This is all multiply divide, so which has the least number? They all are the same, 3, 3, and 3. That's a constant, it doesn't count. So we have to round it to 3. So that's a 9. This has to be a 6. There. I'll leave those there. Might need them again. Okay, 7. The partial pressure of helium in a gaseous mixture of helium and nitrogen trifluoride is the partial pressure of helium. We've got helium gas and nitrogen trifluoride gas together. All right, what's the partial pressure of helium in that system? Okay, it looks like we're not looking for a numerical value. So there's a description that has to accompany that partial pressure. We want the partial pressure of helium. Well, we know that the partial pressure of helium plus the pressure of that gas is equal to the total. Right? That's Dalton's law of partial pressures. So what does A say? The pressure that helium would exert in the absence of the nitrogen trifluoride. That's a good description right there. So A's a good choice. Right. Let's look at the others and see what's wrong with them. The percentage of the total pressure of the mixture that is contributed by helium.
We're not looking for total.
The percentage of the total. When we say partial pressure, we need pressure units, like atmospheres. So we're not going to say percentage of the total. C says equal to the total pressure divided by the helium's molar mass. I don't think so. Equal to the total pressure divided by the number of helium atoms present. Now, there's another possibility. It's not one of our choices, but if we take this and multiply that total times the mole fraction of helium, that will be the pressure of helium. Okay? Remember mole fraction? It's just the ratio of the moles of helium to the total moles. But that wasn't one of our choices. Number 9. Let's see, this is the 31st. So next class will be the 7th, right? Yeah. Okay, we're going to have a visitor next week. The dean's going to show up and see if I know what I'm talking about. Okay, number 9. Which of the following is not a factor in determining the magnitude of the vapor pressure of a liquid? Okay, so all of these except one is a factor in the vapor pressure of a liquid. How about the temperature of a liquid? Let's see, B, C, and D. Temperature. Yep. That will determine the vapor pressure. Increase the temperature, increase the vapor pressure. The strength of the attractive forces between molecules of liquid. Yep. That's true. This is attraction. Actually, let me use the proper term. Intermolecular attractions. What we're saying here is that a nonpolar liquid like diethyl ether versus, let's say dimethyl ether versus methanol. Methanol is polar, dimethyl ether is not polar. So the dimethyl ether, having a weaker attraction for its neighbors, would have a higher vapor pressure. So that is a definite factor. How about C? The size of the container. Size of the container doesn't have any bearing on the vapor pressure as long as there's some liquid left in the container. If you put just a little bit of liquid in the container and seal it, and it all vaporizes, then you don't have an equilibrium anymore. Right? So that would influence the pressure inside, but we can't count it as vapor pressure because there's no liquid. Right? So there's technicality there. And then D is probably true. The type of forces between molecules within the liquid. Yeah, that's another way of saying B. So C is the one that doesn't fit. Let's see, number 10. A liquid is placed in a closed container. Equilibrium is reached when? Okay. Let's say we have a flask and we got a liquid in it and we stopper it. Okay. When is equilibrium reached? We're going to get some molecules. Initially, it's all one direction, right? We get molecules in the vapor phase from the liquid. Once we get enough of them up here, they start going back. And once we reach the same rate, evaporation and condensation are at exactly the same rate, that's equilibrium. And that's when we measure vapor pressure. So, which one of these fits? All the liquid evaporates. You can't have an equilibrium if you got no liquid. So A is wrong. B, when the rate of condensation equals the rate of evaporation. That's exactly what I just said. So that's B. Number 11. Liquids will boil at lower temperatures at higher elevations because, first of all, is that statement true? Do liquids boil at lower temperatures at higher elevations? Yeah. Right. Go to the top of Mount Everest and it'll probably take you about 12 minutes to boil a 3-minute egg because it boils at a lower temperature. I think it was 78 degrees Celsius versus 100. So why is that? What's the difference between sea level and the top of Mount Everest?
Air. O2.
Altitude is less air above you, which means less atmospheric pressure. Right? Less pressure on the surface of the liquid means that the molecules can escape more easily because there's no resistance to their movement, or is less resistance to their movement from the liquid to the vapor. So which statement satisfies that? Number 11. The vapor pressure at which boiling occurs is lower. Yeah. We can establish a lower, actually, when a liquid boils, we've got a balance between the pressure being exerted by the boiling liquid and the pressure over the surface. That's where the balance is. And that's why the vapor pressure at which boiling occurs is lower for a liquid at higher elevations. Number 12. Which of the following statements about intermolecular forces is incorrect? Remember what we mean by intermolecular. Forces of attraction between molecules. If I say intramolecular, I mean the bonds that hold the molecule together. So we're talking about the ones that hold individual, that are effective between molecules. Which one's incorrect? They must be overcome in order for the molecules to escape from the liquid state into the vapor state. Yeah. Stronger the attraction, the more difficulty the molecules have in escaping the surface into the vapor phase. So A is true. A is true. How about B? They're much weaker than intramolecular forces. Is that true? Yeah. What's the simplest evidence for that fact? Propose intramolecular forces are weaker than intermolecular forces. The forces holding molecules together are weaker than those that attract them to one another. What would happen to the molecules? They would disintegrate. They just rip apart because the forces of attraction from your neighbor would just break the bonds that are holding you together. Right? So that's the most logical way of looking at an explanation for the intermolecular forces are weaker than the intramolecular forces. So B is also true. They're electrostatic in origin. Yep. What kind of forces do we have between molecules? If they're polar molecules, we have possibilities of dipole from one and a dipole from the other. Dipole-dipole interactions. Right? Water's a good example. Water is a polar molecule. It attracts to its neighbors through dipole-dipole interactions. Let's see. Well, if you put a soluble ionic compound into a polar solvent, then you're going to get ion-dipole interactions. But if you just have a pure substance, then that's not an issue. What are the other possibilities? What if you have a non-polar compound? What holds them together? London dispersion forces. Okay? So which one's stronger? These guys. They're a lot stronger than these. Because these are permanent, these are temporary. And then within the dipole-dipole, we have a special class that is at the strongest of the dipole-dipoles, and that's hydrogen bonding. So in order to have hydrogen bonding, you need hydrogen bound to some other molecule. Call it X. And X can either be oxygen, nitrogen, or fluorine. And that will give you a dipole-dipole interaction that is extremely strong. You remember why it's stronger? It is the strongest dipole-dipole. 2 reasons. The polarity of the bond is very high. And the other reason is that's just a proton. It's a tiny little thing, and if you have something like, say this, that bond, then this is going to be negative, this is going to be positive, and the neighbor approaches how? Like that. That means, since this is very small, this can approach very close. And the strength of electrostatic forces is proportional to the charge or the partial charge on the object plus divided by the distance between them. So if you decrease the distance, you get a stronger attraction. We can move in very close here because that's just a proton. All right. So I digress. C. They are electrostatic in origin. Yes, that's true. And D. They occur within molecules rather than between. And that's wrong. That's the opposite. Intermolecular forces occur between molecules. 13. Which of the following liquids would London forces be the predominant intermolecular force? What molecules have London dispersion forces? Nonpolar, polar, all the above? All the above. Every molecule exhibits London dispersion forces. The difference lies in, are there other forces that are even stronger? If you have dipoles in your molecule, they're so strong that the London dispersion forces are irrelevant. Okay? It's a matter of degree. How big are the forces? So, when would London forces be predominant? When all other forces are absent. All right? So what we need to do is find a molecule that is not polar. Right? So the first one, hydrogen cyanide, we drew Lewis dot structures, didn't we? Yeah. So I think we drew this one. Right? And this one is going to be polar, that direction and that direction. So that gives you a molecule that's negative over here, positive over here. That's a polar molecule. London dispersion forces are not going to be significant in that interaction. This with its neighbors. How about nitrogen? Completely nonpolar. The only option it has is London dispersion forces. Now we can see that in phase changes. At what temperature does the phase change occur? If the phase change is at a very low temperature, like where you can turn a gas into a liquid or into a solid, at a very, very low temperature, that's an indication that London dispersion forces are the only option it has. And the boiling point of nitrogen is minus 195 degrees C. Very, very low temperature. So that's other evidence. This is theoretical. This is experimental. So B is our best answer. And if we looked at the others, hydrogen sulfide is like water. It's polar. And then IF, right? Fluorine is the most electronegative, so it's going to be polar this way. So polar, polar, polar. London dispersion forces don't matter. Completely nonpolar, that's your ticket. All right, 14. Which of the following descriptions apply to matter in the solid state? Right, we've already encountered one of these, but maybe it's approaching from a different angle. Let's see, A through E. Well, A, B, and C are the unique answers, and then D and E are ringers. More than one or none, right? None. So how about A? Which of the following descriptions apply to matter in the solid state? Definite shape, high density. Yeah. That's true for a solid. B, cohesive forces dominate over disruptive forces. That's also true. And C, kinetic energy dominates over potential energy. That's false. So more than one would be your answer. (15) Which of the following samples of gas would have a new volume of 3 liters if the pressure is decreased from 3 atmospheres to 1 atmosphere at constant temperature? So our relationship here is between the variables are volume and pressure, right? Volume and pressure. These are constant. So what do we got? We got pressure 1 times volume 1 equals pressure 2 times volume 2. So, which of the following would have a new volume? A new volume is 3 liters. So that would be the new volume. This would be 3 liters, right? That's the new volume. If the pressure is decreased from 3 to 1, this is 1, from 3 atmospheres to 1. So there's your unknown. All right? So how many liters? We're starting with this many liters, and we have 3 on top and 3 on the bottom, right? 1 times 3, and then 3 over here. So whatever it is 1 liter of something. The first one, 1 liter of helium. Okay? That's testing to see if you know how to use Boyle's law. 16. Which of the following is a correct equation for the combined gas law? All right. It's got pressure, volume, and temperature there. There are no moles. So normally what I would do is write P1 V1 over N1 T1 equals P2 V2 over N2 T2. But that expression has no moles in it, so we're going to take the moles out. Okay? Now, one solves for P2, then V2, then T2. So we want to solve this equation where P2 is on one side, V2 is on one side, and T2 is on one side. Correct? Just based on the answers. All right, what would that do for P2? Well, P2 means that P1, V1 is still in the numerator. We're going to bring T2 over, and T1 is also still here. Right? So, excuse me, that's not right. Let me try that again. We're holding this one, so this one is, we just kind of flip it. This one's over here. So P1, V1, yes, is still on top. Then we bring T2 over, and we bring V2 over to T1. Okay? Is that any one of those? P1, V1, the first one's not. P1, V1, T2. Nope, second one's not. Third one's not. All right? So that one's not one of them. Now if we do V2, hold that one here, and we still got P1, V1 on top, and we're bringing T2 over, and then we're bringing P2 over to T1. We're not going to find that one in there either because I was looking for this one in any one of those, and it's not there. Right? Yeah. P1, V1, T2 is not there. Okay, so how about T2? Well, if we're going to do T2, then T2 comes over here, and then we leave P2, V2 on top. We bring T1 over, and then, let's see, this one over here, and P1, V1 go down bottom. Like that, right? That one goes over here, that one comes up here, this one goes over there. Okay. Now, P2 and V2 together, P2 is not there. So none of them are correct, right? None of them. That's why E is the answer. All right, 17. When the vapor pressure of a liquid equals atmospheric pressure, the temperature of the liquid equals, A says 100 degrees if the liquid is at sea level. When the vapor pressure of the liquid equals atmospheric pressure, temperature of the liquid equals 100 degrees. Well, that's only if it's water, right? So we're not given that condition, right? We're just said a liquid. So we have to be more general. That's why A is not the answer, because it only works for water. B says the boiling point of the liquid. Yep. When the vapor pressure of the liquid equals atmospheric pressure, the temperature of the liquid is the boiling point. Now, that's the general boiling point definition. What do we mean by normal boiling point? Normal boiling point occurs at 1 atmosphere pressure. So that's either at sea level on average or under some conditions where we can control the pressure. Right. But it didn't say the conditions were not given that would apply to normal boiling point. If the statement says when the vapor pressure of the liquid equals 1 atmosphere pressure, the temperature of the liquid equals the normal boiling point of the liquid. Right, so that I could be sneaky and change that factor. Number 18. All right, intermolecular forces differ from intramolecular forces in that they occur only in liquids. I don't think so. They are much stronger. No, they're much weaker than intra. They occur only when hydrogen atoms are present. Now they're getting at hydrogen bonding there. Right. There's no correct response. Out of those A, B, and C, there's no correct response. In which of the following pairs of molecules would the first listed member of the pair have a higher boiling point than the second listed member of the pair? Okay. A, B, C, and D. Oh, A, B, C, D, and E. So D is more than one, and then E is none. So the first pair is HF and HBr. Second pair is F2 and Cl2. And the third one is O2 and NO. So, which one would, let's see, the first member has a higher boiling point than the second member. What do we need to have a higher boiling point? Stronger intermolecular attractions. So that means stronger those forces based upon polarity or non-polarity. HF and HBr, are those polar molecules? Yeah. Which one is the stronger polar? This one. Simply because, well, actually there are two reasons. HF is going to be polar that direction. HBr is also going to be polar in that direction, but bromine is less electronegative, so this is going to be a smaller value, plus bromine's bigger. So the charge is less concentrated. Bromine is bigger. It can't get close enough to the center of the positive charge on hydrogen to give you a strong attraction as compared to this one. Fluorine is a lot smaller molecule. So this one's going to have a higher boiling point, and A is true. Right? The first one has a higher boiling point than the second one. Since we have more than one or none, then we've got to look at the other two to see if one of those also has a higher boiling point. So how about F2 and Cl2? F2 is like that. I'm leaving out the lone pair electrons, okay? Cl2, excuse me, is like this, okay? Those are both nonpolar, so what forces do they have access to? London dispersion forces, okay? London dispersion forces increase with size. Size of the molecule, size of the atoms. These are bigger than fluorine. So the London dispersion forces here will be larger. That means the second one has the higher boiling point. All right? How about this one? O2 versus NO. Let's see, is that a double bond? I think it's a double bond. Anyway, this one's polar. This one's nonpolar. So the first one has a lower boiling point than the second one. Okay, so this is the only one that fits the conditions. The first one has a higher boiling point than the second one. Number 20. Okay, I got one where we have to look at three choices and see how many of them are true. Okay, yeah, 20. And we have 1, 2, and 3 to see which ones of these are true. Okay, sublimation and deposition are opposite changes of state. Is that true? What's sublimation? What are the phase changes here? Sublimation goes from solid straight to gas, right? Think dry ice, carbon dioxide. How about deposition? Deposition goes from gas to solid. Yep, they're opposites. Right? So this one is true. The second one is a pressure of 1 atmosphere is greater in magnitude than a pressure of 720 torr. Is that right? 1 atmosphere is how many torr? 1 torr is a millimeter of mercury. Right? So, if you're comparing 1 atmosphere to 720, yeah, it is bigger. 1 atmosphere pressure is bigger than 720. How about 3? The boiling point of a liquid can be increased by heating the liquid to a higher temperature. No. The boiling point is dependent upon pressure. Pressure over the liquid. So this one's false. So we have 1 and 2 are true. 2 of the 3 statements are true. That's B. Okay? Oh, we got another one. Looks like we got a series of them coming up. Let's see how we're doing on time. We're good. 21. 1, 2, and 3. Associated with Charles' law is the concept that if the temperature of a gas increases, the volume of the gas increases. That's true. Right? We looked at Charles' law earlier. That's true. Direct relationship between temperature and volume. Liquids, second one. Liquids show little change in volume with changes in temperature. That's true. Yeah. They don't change volume very much with changes in temperature. They have very small changes, which if you're trying to measure a known volume, then the temperature does matter. Number 3, dipole-dipole interactions are examples of intramolecular forces, and hydrogen bonds are intermolecular. Nope, they're both intramolecular forces. So this is false. And the answer is B again. First 2 are correct. 22. Let's see, 1, 2, and 3. First one, both dipole interactions and hydrogen bonds are stronger than most single covalent bonds. That's false. Single covalent bonds are stronger than any intermolecular forces. Second one, the value of the ideal gas constant is the same for all gases under ordinary conditions of pressure, volume, and temperature. The value of the ideal gas constant. Yeah. Is the same for all gases. What we're getting at here is that the gas laws don't care what the gas is. Right? That's one example. The ideal gas constant is the same for all gases. Now, the value itself will change depending on the units. But whenever that change occurs, it will still be the same for any gas that's being measured. So this is true. And 3, both condensation and freezing are endothermic changes. Well, condensation is going from a gas to a liquid, and freezing is going from a liquid to a solid. So when a gas condenses, the molecules get closer together and they slow down. So where does all the heat go? Where does the kinetic energy go? Out, right? It goes out. This is an exothermic process. Same for liquids to solids. You're slowing down to make a solid. That energy has to be dissipated, exothermic. So they're not both endothermic, they're both exothermic processes. So that means only one of them is true. Okay? And we're going to skip a few of those and settle on 25. All right, 1, 2, and 3. Let's see, 1. Water's boiling point is much lower than expected based on comparison with other substances because of hydrogen bonding. Well, water's boiling point is different based upon hydrogen bonding, but it's not lower than expected, it's much higher than expected because of the increased forces of attraction between the molecules. So 1 is false. In the gaseous state, disruptive forces and cohesive forces are about the same magnitude. Disruptive far exceeds the cohesive forces for a gas. Where are they roughly equal? For a liquid. Liquids have roughly equal disruptive and cohesive forces operating at the same time. 3, as liquid surface area increases, the rate of evaporation of a liquid increases because molecules, now that first part of the statement is true. You increase the rate of evaporation by increasing the surface area. But why? Because molecules encounter less external pressure. No, you can have the same pressure on the surface and evaporate faster because you have more opportunities for the liquid to leave the surface. It can be exactly the same pressure, but the rate will be faster until you reach equilibrium. So none of those statements are true. The third one started off to be true, but the explanation turned it negative. All right, number 26. For each of the physical state characterizations, select from the response list the physical state or states to which the characterizations apply. Okay, so if I say indefinite shape, which ones would apply? There's only one that has a definite shape. That's a solid. Indefinite shape applies to liquids and gases. So both gases and liquids would meet that condition. Indefinite shape. Gases and liquids is D. Why don't we do 27 also? This was D. 27. How about definite volume? Solids and liquids have definite volumes. Gases do not. So solids and liquids would be C. I don't know why I left that one out. 28. How about potential energy dominates over kinetic energy? Right? The cohesive forces dominate over the disruptive forces. That is solid state only. Yeah, that's solid state only. For liquids, they're about balanced. For gases, the disruptive, or the kinetic energy, exceeds the potential energy. Oh, there's another one. 29. How about particles are relatively close together? Well, it's definitely not a gas. They're close together in solids and liquids. Right, so that's C. The difference is that in a solid, they're locked in place. In a liquid, they're free to move past one another. But they're still close together. All right, I'll erase these and get to 30. I think we're getting close to halfway. Consider the mathematical expression for gas laws listed. Select the correct name for the law response. Okay, when pressure and volume are the variables, that's Boyle's law. How about 31? When volume and temperature are involved in direct proportion, that's Charles' law. Oh, 32, I don't have it highlighted, probably because it's just an alternate way of expressing Charles' law. Instead of V1 over T1 equals V2 over T2, we say V1 times T2 equals V2 times T1. That's just rearranging the Charles' law equation. That's all that is. Okay, this is where I'm going to pause. We're halfway with the ones that I've assigned, and we'll finish it up next week before that lab.